welcome back to the deep dive. So, if you're a third-year chemical engineering student, you've definitely put in the hours with Python.
Oh, for sure.
You're probably pretty comfortable with it, solving complex equations, boundary value problems, using libraries like, NumPy and SciPy to process data for your reports.
You're a master of computation, basically, in a sense.
In a sense, yes.
But the thing is, a real chemical process, it doesn't live in a Jupyter notebook. It's out there in the physical world.
Right.
We're talking about massive distillation collars, high-pressure reactors, miles of pipeline where things like temperature and pressure are changing every single second.
So for the modern chemical engineer, Python has to do more. It needs to take this huge leap from just being a calculation tool
To be more like an industrial control tower, a full-scale one.
And that is exactly our mission for this deep dive. We're going to show you the fundamental workflow that bridges the gap between your coding skills and real-time industrial safety and optimization.
We're looking at Python as the system-level engineer. It's observing the physical world, analyzing what's going on, and then executing actions, all in milliseconds.
This really is the skill set that defines the next generation of engineers, isn't it?
It absolutely is. I mean, if you want to get beyond spreadsheets and into the world of smart manufacturing, you have to understand this core flow of information. It's the foundation for, well, every intelligent system in industry.
Physical process to sensors.
To Arduino, then to Python, then analysis, and finally, action. We're going to break down every single link in that chain.
Okay, let's start with the why. Let's call this first segment Python, the digital engineer. I mean, we have tools like Excel and MATLAB. They already exist. So why is Python the undisputed champion when a process goes live?
It really just comes down to its real-time capability, and it's architectural fitness for the job.
Okay, take Excel.
Right, Excel. It's great for static data analysis, looking at last week's batch results, but ask it to monitor 50 variables that are updating 10 times a second and then run a safety check.
It just can't.
It fails instantly. It's single-threaded, it relies on someone hitting F9 to update, and it just fundamentally cannot handle the kind of data streams you need for live control. It's obsolete the second you need constant feedback.
And what about MATLAB? I know a lot of our listeners are using it for really advanced numerical modeling.
Yeah.
What are its limits here?
MATLAB is numerically very powerful, that's true.
Right.
Especially for offline simulation. But when you get into real-time data acquisition or automation or trying to connect it to standard IoT hardware, well, those capabilities are often locked behind these specialized, very expensive toolboxes.
So you're paying for functionality that Python just has.
Exactly. You can end up paying enormous licensing fees for things Python handles natively and openly, and that's where Python becomes the superior digital engineer.
It's built for integration.
It's built for it. It excels at continuously reading live data, managing complex automation scripts, and this is the big one. It's the industry standard for integrating AI and machine learning models directly into your control loop. It talks to things like Arduino and ESP32 without any fuss.
And, as engineers, we have to talk about the cost.
We have to. Python is completely free. It's open source. And that's transformative not just for you in a university lab, but for a global company where software licensing can genuinely run into the millions.
So the key takeaway here is that Python isn't just a calculator.
Not at all. It's the flexible, cost-effective, system-level tool that lets you build, monitor, automate, and optimize industrial processes from the ground up.
Okay, so if Python is the brain, it needs good input. That brings us right to the first steps in that flow, the physical bridge. We're talking about sensors and Arduino.
In any chemical process, we're constantly measuring critical variables: temperature, pressure, flow rate, pH.
These are the vital signs?
They're the heartbeat of the process, yeah. And sensors are the specialized devices that convert a physical property like, say, heat causing something to expand into an electrical signal we can actually measure.
And the sources gave some really good specific examples.
They did.
Like for a reactor or a big composting facility, you need continuous temperature data. You might use a sensor like the DS18B20 or a DHT22.
And for safety in pipelines, pressure sensors like the BMP180 are just non-negotiable.
And what about fluid flow?
Well, you're moving liquids, so you need to monitor flow rate. It's critical for your mass balance. Flow meters like the YFS201 are pretty common.
And then there are things like wastewater treatment or fermentation.
Right, biological processes. In those cases, a precise pH probe is what keeps your system stable and active. Even in biogas systems, you're using gas sensors, MQ series sensors, to check for things like methane or CuO.
So all this physical information gets turned into a tiny voltage signal by these sensors, but that signal is still analog. Python lives in the digital world. That's where Arduino comes in, right?
Okay.
As the go-between.
Exactly. The Arduino is the dedicated data collection unit. It's the reliable middleman. It does two things really, really well.
Okay.
First, it reads that analog sensor signal and digitizes it. It turns it into a number, and it does this very, very fast. Second, it sends that digital data, usually over a USB cable, to the main computer.
I think that's a really important distinction for everyone listening. The Arduino is the bridge.
The bridge, not the brain.
Right. It's not doing the complex engineering logic. It's just collecting and sending.
Precisely. It's reliable, it's fast, and it's dumb. On purpose. It just makes sure the data gets from the physical world to the digital world, where Python can do the heavy lifting.
Which brings us to the core of the system, Python-Arduino communication. That moment, the engineering logic actually kicks in. How do you get your professional computer script to talk to this little microcontroller?
You establish what's called serial communication. It's basically a one-way conversation. The Arduino measures something, formats the value into a simple text string, say 45.2 for the temperature, and just sends that string down the wire over and over again.
And Python has to be listening for it.
Actively listening.
So Python gets this continuous stream of text, 45.2, 45.3, 45.1. How does it turn that simple text into a number it can actually use for a decision?
So we go through a very specific four-step process in Python. Step one is just establishing the link.
The handshake.
The handshake, yeah.
Yeah.
Use a function called serial. And you have to be meticulous here. Your port name, like COM3 on Windows, and your speed, the baud rate, which is usually 9600.
They have to match perfectly.
Perfectly. If they don't, you're just yelling into the void and nothing will happen.
Okay, connection established. Now Python is listening. What's step two?
Step two is reading the data. You use a function called readline to just grab that stream of text coming in, but it's still just raw text at this point.
So step three is processing, cleaning it up.
Correct. You have to decode it from bytes into standard text, and then you have to strip away any extra white space or line breaks. Most importantly, you have to tell Python to interpret that text as a number using a float function.
So without that, it just sees the digits 4, 5, and a period,
Yeah.
not the actual value.
Exactly. If you skip that float conversion, you can't do any math. You can't make any comparisons.
Okay, so Python has a clean, usable number, the current temperature. What's the fourth step? The moment of engineering truth.
That's where your training as an engineer kicks in. You apply the logic. This number isn't just for a plot anymore. It's for taking action.
So you use a simple conditional.
A simple if statement. If temperature 60. That one line of code is the foundation of every automated system. And in industry, that doesn't just print a warning, it starts a cooling pump, it sounds an alarm, it initiates an emergency shutdown.
That transition from raw data to if temperature 60, that's really the whole deep dive right there.
It is. It's turning raw sensor input into necessary engineering action.
So let's see this in practice. The sources gave us 4 really distinct industrial applications where this exact workflow is being used right now.
And these examples are why this knowledge is so vital for your career. Let's start with application 1, reactor safety monitoring.
Okay.
In any reactor, temperature and pressure sensors are non-negotiable. Python is watching that data constantly. We don't rely on human reaction time. If the script sees a temperature that exceeds, say, 200 degrees Celsius,
It triggers an immediate action, no delay.
no delay. And that capability is what directly prevents runaway reactions, which is the nightmare scenario in any chemical plant. It's automated safety control.
Okay, application 2, controlled composting and biodegradation. This might seem a bit more low-tech, but
large-scale facilities need tight control. It's all about maximizing efficiency. Python collects temperature, moisture, and gas data codes methane. By analyzing the trends, the script helps operators know the perfect time to aerate or turn the pile. It maximizes the decomposition rate.
application 3 gets into energy, biogas, and POME digesters.
These systems treat waste, often from palm oil mills, and they're very sensitive. Sensors monitor gas flow, methane concentration, and temperature. Python processes all that to calculate the real methane yield the energy output.
And it can spot problems early.
It can stop problems before the digester crashes. A sudden change in pH or gas composition gets flagged immediately, allowing engineers to make adjustments, and that translates directly to more energy and big cost savings.
Finally, application 4, heat exchanger performance. Fouling is a huge issue here.
A massive energy drain. It costs industries millions, so Python constantly reads the inlet and outlet temperatures and flow rates. From that, it's continuously calculating the actual heat duty.
And it can detect a subtle drop in performance.
A drop that's completely invisible to a human operator. That signals fouling is starting. And that allows you to schedule maintenance before the energy efficiency just plummets.
So every one of those examples shows Python connecting real data to safety and optimization. But that means you have a constant, enormous river of data. You have to manage it.
Right. You can't manage a modern plant with a clipboard. You need automated data logging. And that's where the Pandas library is indispensable. Python automatically structures all those sensor readings into a data frame. Think of it like a perfect, time-stamped digital logbook.
And how do you make that permanent and shareable for audits and things like that?
It's just one line of code. You use a function, df.tscsv, and you create a permanent, structured file like reactorlog.csv. You now have a reliable, non-falsifiable record of every data point. No manual error.
Okay, so the data is logged. Now you need to see it in real time. That's matplotlib.
Exactly. While Pandas handles the numbers, matplotlib turns it into an image. Python can generate live plots, like a reactor temperature trend on a dashboard. An engineer can spot instability or a deviation so much faster than by reading a column of numbers.
And it updates live.
It updates as the new data arrives. That's the basis of any modern control room dashboard.
So you've got automatic logging, real-time visualization. All of that provides the foundation for making fast decisions.
And that foundation sets the stage for the next level, for intelligent systems.
This is where AI comes in.
This is where you combine Python's data handling with machine learning, and you transform the system from just reactive monitoring to truly intelligent predictive decision support.
That's a huge shift. We're going from checking if a temperature is over 60 degrees to something else. How does an AI model fit into this?
Well, the AI model is trained on maybe years of historical data. It learns what normal looks like. But more importantly, it learns to recognize the very subtle patterns that come before a major failure.
So Python feeds the live sensor data to the model.
Right. And the model doesn't just check the number against a limit. It evaluates the data point in context with everything else that's happening, and it predicts the system's trajectory.
So the logic changes. It's not a hard rule anymore. It's a prediction.
Yes. The code becomes conceptually simpler, but its power is enormous. It's like AI model.predict current status, imminent failure.shutdown. If the AI predicts an unsafe outcome is coming, Python triggers that protective action immediately.
What are the biggest advantages of these smart systems for an engineer?
I'd say there are three huge ones. First is predictive maintenance. The AI can detect the early signs of fouling or bearing wear weeks before a catastrophic breakdown.
Second would be abnormal pattern detection.
Yes, this is so important. The AI is much better than simple stats at spotting subtle correlations, like a tiny drift in pressure at the same time as a tiny drop in temperature. It sees the ghosts in the machine that signal a sensor is failing or the process is becoming unstable.
And the third advantage?
Automatic optimization. The AI can analyze efficiency in real time and recommend or even apply tiny adjustments to operating conditions to maximize yield or minimize energy use far more precisely than a human ever could.
This is incredibly powerful technology.
Mm-hmm.
But it brings us to our final and maybe most important segment, ethical use and engineering responsibility.
Mm-hmm. Yeah.
If the system is making these critical decisions, who is ultimately accountable when something goes wrong?
The engineer. We have to be absolutely clear on this. AI is a support tool, a very sophisticated one. But it is not a replacement for a human engineer.
It lacks judgment.
It lacks engineering judgment, ethical awareness, and professional accountability. For any safety-critical system reactors, pressure vessels, the responsibility for safety always remains with the licensed human engineer, period.
Which brings up the black box problem. If the AI says shut down based on some complex prediction, how do we even know why?
You can't just blindly trust a model you don't understand. Engineers must have the skills, including Python, to validate and test these AI models. You have to understand the logic. Allowing an automated action without a justifiable reason can lead to catastrophic failure. You have to design for explainability.
So what are the core safety principles we have to build in when we deploy these systems?
You always build in layers of safeguards. Safety checks, manual overrides, redundant systems, alarms. These are non-negotiables no matter how smart the AI is. The key principles are, 1, AI assists, but the engineer has full legal and professional responsibility. 2, engineers must validate the AI models. Treat them like code, not a magic box. And 3, any automated safety decision has to be justified and overseen by established safety protocols.
This has been a true deep dive. We started with Python just solving equations on a computer.
And now we see it integrating hardware, logging data, visualizing trends, and making safety decisions with advanced AI.
The central idea really is the connectivity. Python is the skill that connects chemical engineering theory directly to real-time industrial control.
Exactly. You've learned how Python acts as the decision-making brain and how it integrates with hardware like Arduino, which gives the process its senses.
And as you move forward in your career, this is the challenge that's going to define your practice. And it's the question we want to leave you with.
Given that the engineer must retain full professional accountability for every automated action, how should you design these safety-critical AI-enabled systems to ensure there's always human verification, but without slowing them down so much that you lose the speed that makes automation valuable in the first place? That's the problem you're going to have to solve.